All right, 9.1. Polar coordinates. If you've recently taken trig here, you may have gotten to polar coordinates. It's one of the last topics we teach in trig. Some instructors get to it, some don't. So if it's new to you, don't freak out. It's not that difficult to understand. So it's similar to like we have the rectangular coordinate system, right? There's your x and y axes, right? You pick a point somewhere out here, let's call that point P, and it has coordinates, right? You always plot the x from the origin first, and then from where you end up, you go either up or down to where you y, right? Polar coordinates, similar, except we're not going to have an x and a y. You'd say, okay, that looks like the same picture. Yes and no. So over here, the origin is not called the origin as it is here. Call this the pole. Think of North Pole or South Pole. That's where polar coordinates come in play. It's where you're like on a sphere and you're trying to say, okay, how do I get from the North Pole to some particular country or whatever? Okay, we stand on the North Pole, and then I turn my body into the direction that I want to go towards, right? And then I just start walking if you can. Take a boat or plane, whatever you need to do, but you go in that direction. So the first thing I said, turn your body, right? So that's an angle. We need to know what angle to go from. And then from that pole, we walk out, right? Or we walk backwards if we wanted to, right? There's several ways to do that. So that's what we're going to do here is this is the pole. And this is the polar axis. It's like the initial side that we're always going to start with. Just like in trig, standard position of an angle, the positive x-axis is where your initial side is, and then you rotate either clockwise or counterclockwise, right, to get your angle. All right, so if I say from there, rotate some particular angle and land right here after walking from the pole, the distance from the pole to that point is r. Go figure. It looks just like the hypotenuse in a right triangle, right? When we use x, y's, and r's, it's the same thing. R is the distance from the origin to the point. R is the distance from the pole to the point, same thing. So the coordinates are going to be r comma theta. All right, so unlike over here, we always started with x and then go to y. Over here, we're going to start with theta and then travel for r. If r is positive, you walk along the terminal side of that angle. If negative, you walk backwards, not turn around and walk and on that terminal side. You walk backwards and in the opposite direction of that terminal side. So plot the point 2 comma pi over 4. Now, The angle could be in degrees or radians. You're going to see we're going to start using more and more radians. If you recall, what does a radian mean? Right? It's a comparison of one number to another number, right? Whereas a degree is just a unit of measure. So you're putting that into calculations, it doesn't really work too well. Where you put a radian value, well, they're all numerical numbers, right? Without the units in there. So it works out really nicely when, especially when you get to calculus, to always use radian values. All right, so first thing, draw a picture, right? Start at the pole, plot my angle. So the angle is pi over 4, that's the same thing as 45 degrees. So just do that. And then from here, I'll walk out 2 units along the terminal side because it's positive, so you can just put 2 tick marks to represent that. And that's your point. Now you can get polling graphing paper. What it is concentric circles, like that. I say a dashed or whatever. Those are supposed to be perfect circles. So just go out, in this case, 2 rings, and that's where you would land. Plot the point, -3 pi over 6. All right, so our R value is negative, so I still plot pi over 6. That's first. Pi over 6 is 30 degrees, right? So about like that, there, perhaps. But from the pole, I have to walk backwards. So in this direction, this way, 3 units. That's where we'd be located. Notice I can express the same point as an infinite number of ways, right? Because an angle, you can have so many coterminal angles, right? There's an infinite number of those. So another expression for this point could be right? If this is pi over 6, go around one more full revolution. Pi over 6 plus 2k pi, or 2 pi, in that same R value. Which is equal to -3, and that's 12 pi over 6, is 2 pi, plus one more makes 13 pi over 6. So again, you go around one more revolution, end up in the same location, plot your R, you're still right there. Or I could say, let's put the terminal side over here. Well, the terminal side was 7 pi over 6. My R value would be +3, right? Because we're walking on the terminal side of that. 1, 2, 3. Same location.
Can you explain the 13 over 6 marks?
All right, so here's pi over 6, right? Here to here is adding another 2 pi, right? It's coterminal. So 2 pi is the same thing as 12 pi over 6.
Oh.
And then adding it to the pi over 6 equals 13 pi over 6. All right, so y'all try this one. Given 4n pi over 3. Find other polar coordinates with the conditions r is greater than 0, and theta will be between 2 pi and 4 pi. B, r is less than 0, negative, and theta between 0 and 2 pi. And C, r is positive, greater than 0, and theta is between negative 2 pi and 0. All right, so the first thing you probably want to do is plot what's given so that the answers that you come up with agree with the location of the given point, right? So let me put this in red. Let's see, 4 and pi over 3. Well, pi over 3 is 60 degrees, right? We're looking at something like this. 4 is positive, so you go along that terminal side, right there. So every answer that we get after this should agree with that same location. All right, so this is r is positive. That's easy. 4. But we want our angle to be different. We want it to be one additional rotation past this. All right, so we just add 2 pi to that. So we'll have pi over 3, add 2 pi. So pi over 3 plus 6 pi over 3 is 2 pi, right? That's going to give us a 7 pi over 3 angle. And you can double check it if you want. There is 2 pi, 6 pi over 3, one more is right there. 4 units out, same location. All right, r has to be negative, so we need to put a negative 4. All right, so if we want a negative 4, it means I'm backing up away from the angle that would be formed in quadrant 3, right? So the angle should be in quadrant 3. That's taking the given angle and adding 180 to it, or pi, right? So that's going to be 4 pi over 3, right? Again, you can check that. 4 pi over 3. There's pi, 3 pi over 3. One more pi over 3, we're right here. But my angle is in quadrant 3, but my r is negative, still puts me back in quadrant 1. It's not really a quadrant, it's just you would mesh the two systems together. You can see them there. All right, so now I want my angle to be negative, but my r to still be positive, so that's still 4. I just need to represent my angle being negative. So a negative angle starts here, positive x-axis or the polar axis, and rotates clockwise. So that is, you can tell, if this is pi over 3, this would have been a full revolution of negative 2 pi. So back up one, so negative 2 pi plus a pi over 3. That's negative 12 pi over 3. Not 12 pi over 3, 6 pi over 3. Plus pi over 3 is a negative 5 pi over 3 angle. And so you can see that again. This is negative 3 pi over 3. You can kind of break this up into 60 degrees. It's kind of hard to see. Pi over 3, 60 degrees, right? Oh, there we go. That's negative 3 pi over 3, another pi over 3, 4 pi over 3, another pi over 3, negative 5 pi over 3. All right, so that's how you do those. And again, R is 4, so we're still on that terminal side right there. All right, so let's convert between rectangular to polar, polar to rectangular, and see how that is formed. Let's do rectangular to polar first. All right, so x comma y, let's say is equal to 2, negative 2. Now I have to specifically tell you that this is a rectangular coordinate. If I just put 2, negative 2, that still could be polar, right? You typically don't see negative 2 as an angle, but it could be. All right, so if I plot this, 1, 2, 1, 2. I need to figure out what is the angle formed with the polar axis and the value of r, right? So I could form that angle as a negative angle going that way. I could form this angle as a positive angle going that way. There's several ways, right? Doesn't really matter how to express this. As we know, polar equation, a polar coordinate can be expressed in an infinite number of ways. But if I'm looking at a triangle right there, it's a right triangle, correct? This is x, this is y, this is r, that is theta. There's some relationship between x and y that are given, and theta. What trig function is that? That's tangent, right? So I can say tangent of theta is equal to opposite over adjacent y over x. So now I can say that the inverse tangent of y over x, that value, will give me my angle theta. That's how we calculate what theta would be. How do you figure out what r is? Pythagorean theorem. We're just looking at hypotenuse, right? So r squared is equal to x squared plus y squared. If I solve directly just for r is always positive. It's the square root of x squared plus y squared. All right, so these two formulas, you're going to see they're going to play in a lot of these next few chapters too. We're going to start talking about complex numbers, polar form of all kinds of stuff. You're going to see a lot of it is related. All right, so back to our problem, 2, negative 2. Let's figure out what would theta be. Tangent of theta would be y is negative 2, x is positive 2. So that's tangent of theta is equal to 1. What angle has a tangent value equal to negative 1, that is? If I look at just positive 1, that's a 45-degree reference angle, but we're in quadrant 4. So that's going to be 7 pi over 4 as a positive, or as a negative pi over 4, right? So either one of those, just pay attention to the directions. My math lab typically tells you to leave your angles as positive values and your r as positive values. But if they're not, don't say, you can technically write whatever equivalent coterminal angle that would be. Now r is always going to be the same. There won't be any variation in r unless you're using some other positive or negative to get from on the terminal side or away from it. So that is 2 squared plus a negative 2 squared. 4 and 4, that's 8. 2 square roots of 2. So r theta is going to be equal to 2 square root of 2, comma, pick whatever theta you want, 7 pi over 4. Or 2 square root of 2. And a negative pi over 4. It doesn't hurt to check this real quick just to make sure we've done the calculations. Plot 7 pi over 4. From here, there's 7 pi over 4. Go 2 square roots of 2 out. 2 times the square root of 2 is something. It's right there. Negative pi over 4 is this. And positive 2 square roots of 2 is that same location. All right, so just memorize that. Inverse tangent of y over x gives theta. R is square root of x squared plus y squared. Nothing new, right? All right, let's go from polar to rectangular. That's a little bit trickier sometimes. It's still a formula, still easy formulas. Just you got to watch out for the answers that you get. What you want to do for this is always plot the point first to identify the location. All right, so let's just say 2 and negative 2 pi over 3. That's our r theta. And we want to transform that to xy. All right, so let's plot it. And then we can derive the formulas really easily. Okay, so even if you forget, oh, I don't remember if it's this, I don't remember if it's that, watch how easy it is. All right, so negative 2 pi over 3. That's clockwise rotation. That puts us in quadrant 3, 120 degrees out, right? Like this from that direction. R is positive, so we know we're 2 units down on that terminal side. All right, so our xy that we get, we better get a negative x and a negative y, right? To put us in quadrant 3. All right, so if I look at this right here, I can draw my right triangle right there, right? I have, this would be y, this would be x, this is theta. If I look at some trig function values that involve x, y's, and r's, I know that the cosine of theta is always in the form of adjacent over hypotenuse, right? X over r. The sine of theta is y over x, opposite over hypotenuse r, so y over r. If you cross multiply, this one solves for x. X is equal to r times the cosine of theta. And then this one, y is equal to r times the sine theta. So you just derive these formulas without having to memorize them. Pretty simple, right? So that's how you calculate r, x that is, and that's how you calculate y, given r and theta. So our x is going to be our r value is a 2 times the cosine of a negative 2 pi over 3. Our y will be equal to a 2 times a sine of negative 2 pi over 3. All right, cosine of negative numbers is the same as cosine of positive numbers, if you recall. They're even functions. So just looking at cosine of 2 pi over 3, if you don't remember off the top of your head, use a calculator if you need to, but that should be 1/2. If not, maybe I'm confused. Maybe it's the 0.866, the square root of 3 over 2, right? But you definitely could check this. Cosine of negative 2 pi second pi divided by 3. And put your calculator in radian mode this time, right? Dealing with radian measures. And I hit enter, and that's negative 1/2. So 2 times negative 1/2 is negative 1. We have an x value that is negative. That's good. That's what we needed. The y value. The sine of negative 2 pi over 3, that's the negative square root of 3 over 2. Double check it in the calculator if you wanted to. Sine of negative 2 pi divided by 3. I'll see negative 0.866. Twos cancel. So that's y is the negative square root of 3. So our order pair for x, y is negative 1, negative square root of 3. So always plot, no matter if you're going from rectangular to polar, polar to rectangle, it's always good to plot what's given, plot what you get, your final answer is to make sure it agrees. Let's see if I can find an example to where we got to make some adjustments. Let's convert negative 1, negative square root of 3 to r theta. All right, so you may not necessarily need to physically plot it, but you should identify what quadrant it's in, right? So this is x and y. This tells me I'm in quadrant 3, right? Both of them are negative. Negative to the left, negative down for y. So when I do r, it's negative 1 squared plus all of negative square root of 3 squared. That's 1 plus negative squared is positive, square root squared is gone, leaving 3. That's just equal to the square root of 4, which is 2. R is 2. Pretty simple. Theta. That is the inverse tangent of y over x. Negative square root of 3 over negative 1. That's just an inverse tangent of a positive square root of 3. Now, this is where you got to watch out. Suppose you're like, I don't remember what tangent values, what angles have tangent values square root of 3. Well, you can use your calculator, right? Because I'm using the inverse tangent here. If you recall from trig, inverse tangents of negatives or inverse sines of some angles can put you into quadrant 4 expressed as the negative angle though. So I'm going to put my calculator in just degree mode because I'm not going to recognize the decimal radian. But I'll recognize the degree and I can transform it to radians if I need to. Inverse tangent of a square root of a 3. Square root, where are you? That says 60 degrees. All right, so if I would plot 2 comma 60, which is the same as radians, 2 comma pi over 3. That puts me right here, 2 units out. Right, so that's not our original xy. Our xy is 180 degrees from there. All right, so I needed to adjust this by adding 180 or pi for quadrant 3. So that's why it's really important always to plot these to make sure that they all agree. So 2 comma 240 degrees is the same as the -1 negative square root of 3 rectangular coordinate, or in terms of radians, that would be 4 pi over 3. Another way to express this is not adjust the angle, adjust R. If I was 60 degrees over here, I walked a long positive route. I can go around the negative route by just saying this could be -2, 60 degrees. This is quadrant 3. Same thing with this with the radians, -2, 4 pi over 3. I'm sorry, pi over 3. So again, my math lab may specifically say R needs to be positive, your angle needs to be positive. Okay, so be careful with that. Just make sure you choose, in this case, in radians 2 and 4 pi over 3. So any questions about conversions? It's pretty straightforward. Just watch out for them. Just plot it. You should be all right. The formulas aren't difficult. All right, suppose we have polar equations and I say, give me the rectangular equation. All we're going to do is substitute same formulas we just came up with into our equations and get them in terms of x and y's, or if we want the other way, r's and thetas. So transform equations between polar and rectangular. So all we're doing is looking into a different system. Everybody's familiar with the XY coordinate system ever since like, what, 5th grade maybe? X and Y, easy, something to do. Now we're in another system to where you think about trying to give a coordinates on something that's not flat, right? So a globe or something. This is how you do this. And then next thing we're going to look into is chapter 10. You're going to start thinking out of the box into the complex world. You can't see it. It's imaginary. but calculations still work, you know. But all of this is totally all related. We're doing all the same concept here. Yeah. All right, so let's say transform to rectangular. R is equal to 6 times the cosine of theta. So rectangulars, they're usually like y equals blah, 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 something with x, right? So you see variables x and y's. Polar, R equals something blah, 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 with variable of theta. So all I want to do is I know R is equal to the square root of x squared plus y squared, right? X is equal to R times the cosine of theta. Now y is equal to R times the sine of theta. So I got to use these formulas. I can put in here inverse tangent too if I wanted to, but we were not going to use this one. So here's a trick. I want to make R cosine theta appear in here. Whatever you do to one side, do to the other, right? So I'm going to multiply this times R, and this side times R. R times R is R squared. That's fine. We have R equals the square root. I can square the both sides, and I can substitute that. So this is 6 times R cosine theta. Now I make my substitutions for x's and y's because I have my formulas, right? Here, that equals x. Here, this equals x squared plus y squared. So I have x squared plus y squared is equal to 6x. Technically, I've done what the directions said to do, right? I have no more r or theta in there. Here's an equation that is x and y only, but I'm fine with this. If you get to this point to where you don't have any r's or thetas left, you can stop right there. Because now it's just algebraic manipulation from here to rearrange things. But my math lab does ask you to go into general form. General form means put all the variables on one side of the equation. So x squared plus y squared minus the 6x equals 0. Now I can go a little bit further. You're probably saying, okay, how can I go any further with this? Just putting it in a format to where you're looking at an equation and say, oh, I recognize what that equation's graph would be. You remember completing the square? Vaguely. Okay, so we're going to group the x terms together. And I'm going to add in some number here to make a perfect square trinomial. We get to add it in right there. Remember half of b. Then we square that answer. So this would be half of our b is -6. So that's -3, and we square it, gives a +9. So I add 9 into this left side. Oops, it's not a 6x. If I'm adding 9 to the left, I better add 9 to the right. All right, so if I factor the first 3 terms, the first 3 terms would be x plus x minus 3 times an x minus 3 when factored, right? So this is in the format x minus 3 all squared plus y squared is equal to 9. Everybody recognizes the format of that? It's an equation of a circle. X squared plus y squared equals r squared. And if I adjust x and y by adding or subtracting, that tells me where the center is. So this has a center of 3, comma 0, nothing being subtracted or added to the y, right? And radius of 3. I won't actually go that far, okay? So, like I said, once you have an x and a y, you're good. I don't need it in a special format. If you wanted to check this in a graphing calculator, you can do that. You can see that you can put your calculator in polar mode, which we'll use this a lot in a minute. So scroll down to the 4th row. So like POL, polar. When you go to y equals, notice everything is r equals now. You can just type in exactly what that formula was. What was it? What we had? 6 cosine theta. When I hit the variable x, it puts it as theta. Oops, I had the wrong thing. Go back. There you go, it puts theta in there. And when I graph it, I may have to adjust the windows. I think so, yep. Adjust my window. I'm in 0 to 2 pi. That's 2 pi right there, right? So on my mode, I need to be in radian mode. There we go. And there's a circle. That's supposed to be a circle. It kind of looks like an oval. That's just because your screen is rectangular and it's not square. You could do a zoom square and it would adjust your dimensions to where you see the actual picture. Number 5. To scale. So that's a circle. And you can see right there, your radius is at 3, 0. I'm sorry, your center is at 3, 0 with a radius of 3. All right, transform to polar. These are probably easier because we know exactly what x is in terms of polar form. We know what y is in terms of polar form. X is equal to r cosine theta. Y is r sine theta. So just make those substitutions. R times 4 times r cosine theta. Y r sine theta is equal to 9. Simplify a little bit. This is 4r squared cosine theta sine theta equals 9. Again, this is fine with me. You've done the directions. But we could make this and transform it into something else, perhaps. Typically, usually only have one trig function in there, maybe. 4 could be rewritten as something else, right? I could say it's 100 divided by 50, right? If I wanted to, or 100 divided by 25, that is. But I'm gonna just say that's 2 times 2. Make it a little bit as simple as possible. Like, why am I doing that? Do you recognize something we just had? What is 2 times the cosine of theta sine theta? It's a double angle formula, right? That is the sine of 2 theta. That's sine of 2 theta times the 2 times the r squared. equal to 9. And that's about it as far as I can go. I can put the 2r squared in front of the sign. That'll be more typical, right? If I wanted to solve for r, we could do that. That's r squared is equal to sine 2 theta over 9/2. Divide everything by sine 2 theta.
Big 9 once.
9,
No, wait, you're using the 1.
yeah, dividing by this number first. I could have divided everything by that. Let's do it that way instead of doing double divisions. So I'm going to divide by the 2 and the sine 2 theta. So that's 9 divided by 2 sine 2 theta. Instead of getting that complex fraction. Take the square root of both sides. That gives me r. Good enough. All right. It's just mechanics from here. All right, any questions? This is one of the simplest sections, I'm telling you guys. If you don't do the plotting the polar coordinates too often, sometimes you might forget it when it comes down to the test, and it might be a couple of weeks or something. But once you start back out, you're like, oh, okay, it's really easy. Just remember, if r is positive, you walk along from the pole out on that terminal side. If it's negative, back up away from it. All right, let's do, I'm going to go right into 9.2. It's a very short section. I don't do a whole lot of really testing for 9.2. You might see one question or two in there, but it has a lot to do with the graphs of polar equations. I will not make you graph anything.